Swayam Prabha. Digital India. Educated India.
Now, I would like to argue that the scheme is secure. So, does everyone remember what the adversary sees in the security game of public key encryption? Basically, it sees the public key and it sees a ciphertext, right. The ciphertext corresponds, in our case for simplicity, since we are just thinking of 0 and 1, right. The ciphertext encodes either 0 or 1 as the message bit, and the attacker has to figure out which one it encodes. Do you all remember this? So, the attacker gets to see the public key and a ciphertext for a random bit, and it has to guess the bit. Okay. So, I will just write this. So, the attacker, recall, the attacker sees the public key, obviously not the secret key, right, the public key and a ciphertext for a random bit, yeah, and it must guess bit. So, it can always guess the bit with probability half, and we will ask for it to do non-negligibly better than that. Okay. So, now I want to prove security based on this learning with errors assumption. Okay. And I am going to use the Hermite normal form, obviously, because in my scheme also I sampled the secret from the error distribution, right. So, we sampled S from chi. So, I am going to use LWE to argue security. How should this argument proceed? Does anyone have any thoughts on how to get started? So, okay, let's try to build it together. Okay. So, what was our public key? It was A, and it was Y transpose, which is S transpose A plus E transpose. This was our public key, and our ciphertext is going to look like AR plus X and Y transpose R plus X prime plus M Q over 2. Okay. So, here M is a random bit. So, this is what the adversary sees. Okay. And once again recall that S, E, R, X and X prime, everything is sampled from this error distribution. So, now how should I argue that this ciphertext is hiding this bit M? That is exactly right. So, I mean, very good. So, let's try to say that more clearly. If I could show that the part of the ciphertext which encodes the message, if I could show that Y transpose R plus X prime is indistinguishable from random, then I could say it hides the message, right, because if it is random, then it is just a one time pad which will always hide the message. So, my goal is to show that Y transpose R plus X prime is random. Now, how can I show that? So, this is the way to think about security, right. Start with what you want. I would like, my only goal is to hide M here. So, if I want to hide M, I want to argue that this pad which is sort of masking it it's a random pad, like a one time pad. So, I want Y transpose R plus X prime to be random. Now, can't I apply LWE to this and change this to random? What do you think? We cannot in fact use LWE here, because for the LWE problem I need Y to be random, but is Y random? y is also not random. So, I need to argue this in steps. Okay. So, once again we will use this hybrid argument which we have seen in the past. So, what we do in the hybrid argument is we look at the distribution of the real world scheme. So, when I say distribution, you know, we are really thinking of what does the adversary see. The adversary sees some distribution, right. It is a public key and a ciphertext. So, one nice thing about encryption is that this distribution is very easy to state. As you build more sophisticated schemes, you know, these distributions become really complex and hard to reason about, but right now it is very simple. So, what all does it see? It sees a matrix A. This is always random, no problem, nothing, you need to argue nothing. It sees a y, a vector y, okay, and then it sees a ciphertext which contains, you know, this vector which we were calling A and this element which we were calling B. So, it sees these 4 things A, Y, small a and B, okay. It sees these, and my goal is to make this YR plus X prime as random. So, what will I do? Currently, I cannot immediately shift it to random because there are dependencies which I need to first break, okay. So, what I will do is, this is, you know, my starting point distribution. So, let me say this is my hybrid 0. So, you know, this is my starting point distribution. What I will do is, I will simply you know, modify it a little bit. So, what can I do in order to modify it a little bit? Well, I can you know change the public key. So, I can change the public key to some a comma random. Okay, so, what did I do? I replaced y with random. This is the first change I made. You should see why I am doing this, right. It is because I can apply LWE to the ciphertext once my y is random. Now, whenever you make this argument that I will change this to random, you have to be very, very careful that you did not disturb any dependency. So, for instance, I cannot just change the ciphertext to random at this moment, right, because of what we said. So, we have to argue that I did not hurt anything else by making this change. And how can I argue that? Well, A is anyway unchanged and the ciphertext can be computed just given y. So, what is the dependency of the ciphertext on y? It just takes a y and computes on it. It is some function of y. So, I can change y and I can compute the ciphertext as a function of y as before. So, that is why this is okay. So, this will hold by LWE, okay, and remember this is that short secret version of LWE. So, this is my first hybrid. Now, my second hybrid is, any guesses? So, now I will you know, I will change my ciphertext to random, right. So, okay, I mean if you want to be sort of really careful, you can also insert an intermediate step as I have here in my notes. So, you know, let me call this as pk tilde, this fake public key. So, now I can say that I am computing a fake ciphertext using this as A B prime plus M Q over 2 mod Q where A and B are random. Okay. So, I am now, yeah, I am A and B prime, sorry. So, this is, you know, this is A, right, and this is B. now what am I doing? I am changing A and B prime to random. So, B used to be, or B prime, what we are calling B prime, used to be y transpose r plus x prime. I am changing that to random. I am also changing AR plus x to random. Okay. Now, I can again do this using the learning with errors problem. So, why is it that this is just the learning with errors problem? Because you know, I can write the ciphertext as A y transpose r plus x x prime, okay, plus 0 m q over 2 mod q. So, now what I am doing is that this part, this yellow part, I am applying LWE to that. Now, note that I can do this because A is random, Y is random, and R, X and X prime are chosen IID from the error distribution. So, there are no dependencies on anything. So, once I do this, what did I get? So, now what did I get? So, now my ciphertext is, it is A and B prime plus m q over 2, okay, and my public key is A and Y, which are already random, okay, and moreover this A and B prime are also random. Okay. So, this is what I have now. So, now in the next hybrid, okay, I can change B prime plus m q over 2, I can replace this, you know, just by random. So, basically I can just wipe out the m, and this is, I mean, this actually does not even need a new hybrid, it is obvious already in the previous one. I mean, I have m being masked by a random element. So, the distribution of m plus random is still random. So, at this point the adversary does not see the message at all. Okay. So, the advantage of the adversary at this point is exactly half, as long as LWE holds, right. So, assuming that LWE holds, you have completely erased the message bit from the ciphertext. So, the advantage of the adversary is half, it cannot be any more. Okay. So, this is the proof. The question is, you know, why does changing Y not alter the ciphertext? So, this is very important. So, let us look at hybrid 1, okay. My claim is, you know, let us actually insert a hybrid 0.5 in which, you know, whatever pk you have, okay, and the ciphertext is simply a function, you are explicitly writing it simply as a function of the public key. I mean, this is already happening in hybrid 0 as well, right. So, even in the real world, the encryptor only gets the public key. So, whatever it does with respect to the public key. So, what I am saying now is that if I change the public key, right, the rest of the distribution can still be generated. See, what could have been a problem? Now, my Y has S in it, right. If, let us say, you know, as a thought experiment, if let us say I am in the private key encryption setting and my ciphertext also makes use of S in some way, then I cannot say that the dependency goes away, then I cannot change Y to random because that S is also lurking somewhere else. So, if I change Y, I cannot generate the rest of the distribution with the new Y, but here we are okay because it is a public key setting and I can write the ciphertext entirely as a function of the public key. So, just as a conceptual change, as I said, you think of hybrid 0.5 which is in the middle, what does it do? There is a public key and there is a function of the public key. So, you know, it just has pk and f of pk. So now if I change pk, I can generate f of pk, no problem, right. So the important thing is that to sort of see where it could have broken. I mean, if my ciphertext were not f of pk but f of pk comma s, then I would be in bad shape, right, because then I cannot do this. But having changed the public key to random, I can generate the ciphertext accordingly, and now I can apply LWE on the ciphertext. So now you asked me a question, now I will ask you a question. I replaced everything by random. Why will decryption work? My public key is all random, my ciphertext is all random. So I hid the message, but why does decryption work? Is that right? So the answer is it is still bounded by 0 to q. So let us see. So now my public key is A, random y, okay. My ciphertext is random A and random B, okay. My decryption is what is it? It is some S transpose B minus A, something like that, right. Forgot the notation. Yeah, whatever, plus minus always okay.
B minus S transpose A.
Okay, that matters, you are right, good. Okay. This works? So I claim that since A is now random, S transpose A is also random and B is also random. Therefore, I claim that this whole term is random. So why is this all right? Because this is not the scheme. This is the proof, which is a thought experiment. Yeah. So the scheme is what we saw, where you have you have these algorithms. The proof is only concerned with the view of the adversary. So in the view of the adversary there is no S, there is only a public key and a ciphertext. So what we are arguing is that the distribution seen by the adversary is indistinguishable from random based on the hardness of the underlying problem. Okay. So there is no burden of correctness on what the adversary sees, because the adversary never gets to decrypt anything. All right. Okay. So are there any questions? Yes. No, the question is that we said that y is not random, that is because we know about S, that is the question. So the question is, why is y not random? Y is not random statistically. This is actually also a very, very good question. It has, this question has important sort of implications. So what is our y? Okay. It is, let me get the transposes right. So it is S transpose A plus E transpose, okay. Now A is a square matrix, so this is n by n, right. So S transpose is like this, right, plus E transpose, right. So the question is, why is y statistically not random, right. So now so this is actually a question of asking, why is a learning with errors sample not random already, right. Why is an inner product perturbed by noise already not random? Can anyone answer that? The perturbation is very small, but moreover, so here I am also given A. right. So, if I were not given A, then I could argue that S transpose A is random, but I am given A. So, if I am given A and S transpose A, then I can recover S, is not it? So, I cannot say that Y is random. See, note that I am going to use this public key to generate many ciphertexts, right. So, if I do not add noise to it, then I can simply recover the secret key, right. So, therefore, I need some I need to argue somehow that this Y is not leaking the secret key. So, for that I add this error, right, and I use LWE to argue that this is random.